Hello, welcome to this video looking at polygons and their characteristics. This video is targeted at students in Essential Math 40S, taking the Geometry and Trigonometry unit. And this is looking at polygons, which is the last lesson in that unit. On the front page here, you can see I've put a picture that I got from greatlittle.minds.com of different types of regular polygons. A regular polygon, and we only look at regular polygons, is a polygon that has all sides of equal length. So a polygon is a figure that has some number of straight sides that all connect and make a closed shape. And then a regular polygon, the regular means all sides are of equal length. So a triangle, you have to have three sides in order to make a shape that can enclose an area. So a triangle has three sides. It's the smallest number of sides you can possibly have. And then it goes up, 3 sides, 4 sides, 5 sides, 6 sides, and so on. Some of these are common, and you'll have heard the words before. Triangle and square are pretty common. Pentagon and hexagon are fairly common. Octagon is also fairly common. And some of these you might not have heard of. A 12-sided polygon is called a dodecagon. Typically on the exam, they do expect you to know how many sides the common polygons have. So triangle, square, pentagon, hexagon, and octagon with 8 sides. And if they start using a weirder polygon, they'll usually tell you the number of sides. What we're going to look at in this video is what you can calculate on a polygon, how to use each of the formulas associated with polygons, and what it is you're actually calculating. So we'll start with the size of a central angle. A central angle in a polygon is an angle that's created if you go to the center of the polygon and you make a line, and please forgive my bad drawing on this tablet. If you basically cut this as a pizza where one whole side of the polygon would be the crust and you cut it to the central angle would be this angle found in here. And it would be the same no matter which slice of pizza you looked at. That central angle would be the same size. All the way around is 360 degrees. So to figure out how big one of these is, you just have to take 360 degrees and divide it by the number of sides. So this is a hexagon. There are 6 sides. So the size of a central angle here would be 360 degrees divided by 6, or 60 degrees each. So each of these angles in the center is 60 degrees. This polygon has 1, 2, 3, 4, 5, 6, 7, 8, 9 sides. This is a nonagon. So in order to figure out the central angle size on a nonagon, you'd go C equals 360 degrees divided by 9, and 360 degrees divided by 9 would be 40 degrees. The more sides you have, the smaller the slice of pizza would be, and the smaller the central angle gets. Okay, this next one is the sum of the interior angles. The angle formed by 2 sides is called an interior angle. So that angle there, this angle here, all of these are interior angles. Not to be confused with central angles, which are still inside the shape, but right in the center. Interior angles are the angles formed by the sides. They're the same all the way around. How they're calculated is you take 180 degrees times the number of sides minus 2. So to get the sum of the interior angles in a hexagon like this, it would be 180 times 6 minus 2, because I have 6 sides. Now the brackets tell you to do that first. So you get 180 times 4. So you get 720 degrees. So if you added all these up, that's what sum means. If you added them all up, the total would be 720 degrees. If you want to know how big one of them is, you just divide it by the number of angles, which I'll show you on the next slide here. On my nonagon, again, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 sides. I would go 180 times 9 minus 2. Do what's in the brackets first, so you get 180 times 7. And 180 times 7 is 1,260 degrees. So that would be the size of all these angles all the way around added together. Now, in order to get the size of one interior angle, if you want to know how big just one of these angles is, you take the sum of all of the angles that we got on the previous slide and divide it by the number of interior angles. So if we look back, we saw in our hexagon, all the angles added up was 720 degrees. So we just take 720 degrees and we divide it by 6, because there's 6 interior angles, same as the number of sides. And 720 divided by 6 is 120 degrees each. So each one of those interior angles in a hexagon would be 120 degrees. In my nonagon, I would take the sum of all the interior angles, which was 1260 degrees. And I go 1260 degrees divided by 9, because there's 1, 2, 3, 4, 5, 6, 7, 8, 9 interior angles, same as the number of sides. And 1260 divided by 9 is 140 degrees. As the number of sides increase, these angles will increase as the spread between them gets bigger and bigger and bigger. Next is diagonals. A diagonal for a polygon is any line inside that joins one corner to another corner that is not adjacent. So that's a diagonal. So is this, because these are non-adjacent corners. So is this. I missed a bit. Those are non-adjacent. I wouldn't attach this corner to this corner because they're already attached with a side, so they don't have a diagonal, nor does this one. So I'm going to get all those off of there. In order to calculate the number of diagonals you'd have, you got a bit of an uglier formula here. The number of diagonals is number of sides times by the number of sides minus 3 divided by 2. So in a hexagon with 6 sides, I go 6 times 6 minus 3 divided by 2. Again, anything in the brackets has to be done first. So 6 minus 3 is 3. I get 6 times 3 over 2, which you could type into your calculator. It's 18 over 2, or 9. I'm going to try to draw them in here. Starting here, there's 1, 2, I'm not very good with this tablet, 3, now going to here, 4, 5, 6, going to here. There's 7, but we already have a line there. So here's 7, 8, and then down here, the only one we don't have is this, 9. This is a very messy version. There's a nicer version of it drawn in your book for a pentagon, but there are 9 diagonals in this shape. For a nonagon, the number of diagonals would be 9, because there's 9 sides, times 9 minus 3 over 2. So you get 9 times 6 over 2. 9 times 6 is 54. So you can do this on your calculator too if you want. You get 54 over 2, or 27 diagonals. I'm too embarrassed to draw all the diagonals. I'll do it from one point. We got 1, 2, 3, 4, 5, 6 off of that point. You go to the next point and just keep attaching corners that are non-adjacent that don't already have a line. Eventually you'd get 27 lines in there. Now for lines of symmetry, calculating the lines of symmetry is easy. What's difficult is drawing them. The number of lines of symmetry, and I'll tell you what that is in a second, is the same as the number of sides. So a hexagon having 6 sides will have 6 lines of symmetry. A line of symmetry is a straight line that cuts this shape exactly in half. So if you folded it over the line, the 2 sides would match exactly. In any even-sided shape, like a hexagon has 6 sides, that's an even number. So in any shape that has an even number of sides, your lines of symmetry go through the corners. So there's 1, sorry, let me try that again. 1, 2, 3. Okay, there's 3 lines of symmetry, But then this cuts the shape in half too. 4. You can see if you look at just that vertical line, that cuts it exactly into two symmetrical sides. 4, 5, and 6. So if you're drawing lines of symmetry on an even number of sides shape, like a square, hexagon, octagon, anything with an even number of sides, you connect the corners and the middle of each side. Okay? If you're trying to draw lines of symmetry on something that has an odd number of sides, my nonagon here will have 9 lines of symmetry. You don't connect corner to corner because that would not be symmetrical. You can see if I do that here, and I'll get rid of it in a second, that does not cut my shape perfectly in half. If you have an odd number of sides, you go from a point through the middle of the side opposite. It's actually easier than this because you have one for each point. So there's 1, 2, 3, 4, 5, and it looks like it's done, but you still got points here. 6, 7, 8. This is much easier on paper. And 9. Ugh. Okay, so 9 lines of symmetry. And that's all you're going to have to calculate. There's 5 things, 5 formulas. Make sure they're on your cheat sheet and draw a little picture for yourself to help you understand what it is you're calculating. I hope this video helped, and thanks for watching.